Yeah, thank you for the welcome, and welcome to our presentation where we discuss a solution approach, how we integrate the monitoring of an Openshift cluster into the world of Icinga. We already had these days many interesting discussions about how to monitor Kubernetes, and we are happy that we can contribute here with another quite practical discussion, showing us a use case. We developed, thanks to a many years lasting collaboration with Michael from RTL2 and we from Würth as a partner of Icinga, where we act as a solution provider for monitoring solutions. So I just want to give a few words, if this is working, about ourselves. So quick presentation. Patrick Zambelli, my name. I am part of the monitoring consulting team at Würth where we are working to deploy monitoring solutions for the Würth Group, but also for external customers. Würth is quite known as a company providing craftsmanship services and construction area stuff. We are an IT company and doing ERP projects, CRM solutions, and in our unit, we do also monitoring projects for a while. We have a solution which is called NetEye. And based on this solution, we do our projects based on Icinga today. We already started in 2008, many years ago, using Nagios at that time. So what I've learned yesterday, I'm also one of these who are still knowing what cacti is, or cacti. And today, as a partner, with Icinga, we do monitoring projects. We enrich this solution by additional modules. We found out which are useful to integrate additional features into this world in order to make our projects and complete the use cases. And some of them, we also publish them as an open source project outside.
Yeah, welcome everybody. My name is Schabatin. I work as a system administrator at Ready Computer at RTL2 TV. Ready Computer's goal is fulfilling all the needs of the TV station, from first to third level support, planning, designing workflows, and developing highly customized solutions. Since 2017, we are partners with Würth and Patrick and I, we invented Icinga 2-based monitoring at RTL2.
Yeah, what we want to talk today is Michael wants to present at the beginning the container-based approach. What are the advantages and the motivations in RTL2 to adopt this approach? Next, I want to highlight in a more technical level the strategy to apply Prometheus and alertmanager for monitoring in the Openshift cluster, and concluding the way how to bring this dynamic world into a world of Icinga and make these two worlds merge together. So, Michael, let me start.
Why RTL2 decided for Openshift and the container-based approach? First things first, let me keep up the things from yesterday. Yesterday we learned to hate Kubernetes. I think everybody of you remembers. Then, due to the evening, we learned to neutralize it. And today I'm here and will share my love for Kubernetes with you. Maybe. Okay, so in 2001, RTL2 started with a monolithic concept with its own data centers, everything on-premise. And we started developing this custom solution for the TV broadcaster. As we heard so many benefits or bad sides from the container world, I won't go through all these topics now, because everything was said, and we hate, neutralize it, and love it. So there we are. Let's jump further to the questions we had discussed at RTL2 and why we decided this. First of all, before the pandemic, all this cost efficiency, energy efficiency, all this stuff came up. Then the pandemic came around, and we lost some employees too. While all this happened, we started with a little Docker environment and tried out the world of containers and found, well, we are highly limited with only Docker. We need some orchestrators. And as a matter of fact, RTL2 is an enterprise environment. So we took a look at Kubernetes standard. We had a POC on a vanilla installation. We had a little look at Nomad or even Docker Swarm. But in the end, our long-term partner Red Hat brought the solution as an enterprise solution, Red Hat Openshift. This brings me to show you in detail the RTL2 main application called Bobby. Founded in 2001, a very German name, Bestandsobjekte. You like it? Let's call it Bobby again. I think it's better. Yeah. Bobby is a custom database management and orchestration system developed for RTL2 that is now used to handle the entire channel business. To fully understand this, you have to take a look at the channel business in the German-speaking market. Among other things, we live from licensing finished products like films, series, and formats, and then exploiting them accordingly. This initially simple process is fully mapped in the RTL2 database. For example, the broadcaster buys a format or a series from the US market, let's say Game of Thrones at HBO, and it's on us and in our database now to fulfill all the needs the TV station has. So all purchased episodes will be loaded into the video archive and assigned an internal RTL2 ID, which is then required for further processing. Then additional decisions are made. In example, broadcasting times, advertising planning, but also youth protection and legal clarification. Edited versions are then created and stored in the archive. You can imagine, we have an edited version from Game of Thrones, age 12. We can show that in the early afternoon, like 3 o'clock. Children like. But we have the original version from Game of Thrones 2 with all the naked women, and we can show this late night. This means our database is able to handle all this scheduling. After the broadcasting, we can measure all the broadcast relevant data and bring that back to the database for further scheduling. This brings us to the concept. This database solution depends on 45 plus sub-applications or minor applications all around this database, from planning, licensing, video editing, everything is in there in kind of self-written sub-applications. This brought us to the conclusion, yeah, we can containerize this. Even if you can read it, the product is built on JBoss and Wildfly. So we started in 2001 with 24 bare metal nodes. Testing, integration, production are highly separated in closed environments. The idle time in our data center went up to 90%, even in the peak hours. You remember I told you cost efficiency, energy efficiency? There we are. Openshift now brings us down to 10 bare metal nodes. Testing, integration, and production is separated in namespaces, all in one environment. And in peak time, we only have 25% idle time. We are efficient. This brings us to the next point and why we are here all today. We will talk about monitoring. We needed some solutions and some strategies to monitor and display all the new dynamic values of a Kubernetes environment. As I mentioned before, we heard so many things about Kubernetes the last 2 days that I will keep it short here. I think you can read. Everything is said already. It means Openshift brings us dynamic workloads, dynamic infrastructure. You don't have to care where your pod or container is running. The orchestrator will do and handle everything for you. This brings me to the point that we started thinking about monitoring and how we can handle all these resources in a good way and meaningful. We found out Prometheus is the built-in monitoring stack, but it's very, very complex. This is the thing we heard already too. It's so complex that we needed a solution to summarize and visualize all the information we need at RTL2 and for our developers. So we started thinking about Prometheus and watching it closely. We found out Prometheus pulls metrics provided by the various resources via HTTP Prometheus exporters. These metrics are recorded according a time-oriented dimension, a time series. A time series is a stream of values belonging to the same metric with the timestamp at which it was recorded, and so on. Prometheus also provides a store for all scrapped samples and runs rules over this data to aggregate and generate alerts. Now the alert manager comes into play. And for us, Grafana is the best tool to visualize all these collected metrics. And with this, I will give back to Patrick to show you some PromQL stuff.
Yeah, more in detail, we started to investigate how to get this data out and start working with this data to get some, let's say, monitoring out of it. And we learned metrics are the part which is indicating us how an application is behaving. So if we have an application like a web server, we can understand from the metric what is the number of requests which is coming in. Oh, how long does a user has to wait until something is being replied. These metrics are stored in the time series database. Thanks to the Prometheus query language, we can also filter for this data. So by the labels, which is the key value pair, so the job, the namespace, and everything we can understand, we can extract meaningful data and narrow the search to something which is really of interest for us. Additional operators allow logical and arithmetic operations, and therefore we can also apply some calculations, like in this sample example, compare the free memory of the system to the used memory, multiply it by 100, and we can easily see, 94% utilization, so this test system is really running bad. We don't have much resources, but it explains us this is a number from where we can start working. And we started to understand that the alert manager allows us to exactly use these Prometheus query language expressions and define the alert manager rules from where the alert is fired, and we can extract and fire the notification to a third-party system. To let you understand this concept a little better, we prepared a very simple application where we can trigger the alerts and introduce our simple container application, which consists of a Prometheus sample app. This is a web server exposing an HTTP address. This is our so-called deployment. The deployment is activated and published via service on the network, on the internal network of the Openshift cluster. So far, so good. The server is running, and it's exposing, as typical applications in Kubernetes or Openshift, the metrics. The Prometheus is now coming into play. So with the service monitor, we activate the discovery and start pulling these metrics into our system. The application, the web server, is exposing numbers like response time and so on. And for us here, was of interest in example, we want to see how good are the requests served. What are the HTTP request codes collected? 200 is okay, 404, we have a problem. And exactly that's the stuff to show you here in a concrete example we want to keep under control by an alert rule in Prometheus. So we have the, maybe I can show it here, the metric. By some filter application, we want to filter for a job and the error code 400. In the last rating 1 minute, so the rate method specifying over the 1 minute is higher than 1. And what we could have, if this line here is indicating, errors are coming, we would have an alert in the monitoring. And in this case, the world of Icinga, where the namespace, for example, could be the name of the host, and the alert rule, the problem that is appearing. But how can we make this mapping? And why we would do this mapping? The use cases we developed over the last years are bringing us in the situation where we have a holistic monitoring over IT infrastructures. So IT infrastructures are monitored by the network, by servers, virtual infrastructure, and therefore we have already now central alert dashboards. IT operating teams are working on that dashboards. We have notification logic, and obviously the management wants to have also reporting availability, how good does the services work. So the need is bring this Prometheus world into the Icinga concepts and obtain the unified monitoring as an umbrella system and identify a way how to map such dynamic environments where deployments of multiple replica sets, pods that are coming and going, are somehow anyway condensed into such a concept which is the object of a host and service in Icinga. So we understood that the alert manager in Prometheus is sending lots of alerts. The alerts can be of multiple quantity and different types. So we have deployments, we have network, we have services, and therefore the number can be very dynamic, wide, and large. The alert manager now has some nice capabilities, and one of the interesting one is the grouping capability. So we can aggregate these incoming alerts by labels. As we have seen before, it could be the deployment itself, that it's the key value pair to group this information together and bring this into an alert group. Other attributes like the inhibit, let's say we can define the group weight and the group interval, are attributes we know also from Icinga. For example, a soft state and a hard state. So I don't want to notify the first problem, but let's wait for some seconds or minutes, and if the alert still persists, only then send it out. These are the settings of the inhibit or the re-notification to optimize also the quantity, let's say the flooding of alerts I'm going to send out. Our idea was to take this alert group, send it to a webhook consumer, and care about duplicate events. So we need to know about what is already being alerted 2 minutes before, because the alert group may consist a large number of elements that have already been sent before. And we need to iterate over the group itself to come to a single alert information saying, this is good, this is bad, this is a recovery. What we applied here is a module called Tornado from NetEye, which is generating single alerts and sending them to the Icinga. Tornado. What is it and why we use it? It's a module here to process events. It's an open source module we have developed in NetEye, and it's exactly here for the purpose whenever I have events coming in where I cannot control directly when the event is being generated. So I cannot do active polling because it's a black box system, it's closed, and I cannot control when I will receive the events and the problem. Or I have the situation like in Openshift, the system has its built-in monitoring concept. So Prometheus is the third-party system. We want to interact and consume exactly these events. To make it work and integrate into the concept of NetEye with this Tornado, Tornado is quite flexible and is made of 3 main pillars to start interacting with such incoming events. The first, on the left side, is the collector. The collector part is responsible for consuming the incoming protocols and sources. It can be syslog, webhook, whatever. The main focus is to obtain one standardized object in a JSON format. This is exactly this gray box in between. So we can normalize all incoming events to start the matching process. With the matching, I want to understand, what is the source? Is this an SNMP trap from the network? Is this a server or is it an Openshift event? So I optimize with the filter the direction for consuming the event, and afterwards I can work on extracting the data, manipulate it, and finally generate the action, which is the executor, for example, an Icinga API call, and Icinga is then the destination for creating such objects. That's the theory. How this could look like now, we have here the situation, alert manager. Alert manager receives more 404 alerts. I hope you can see it. This is the error code of the 200 and the 400 ones. And if this number rises, the alert manager, with the query in mind, will fire the problem. Once this is firing, the webhook is sent to Tornado. I will first of all catch this event and obtain my JSON object. The JSON object is quite long. We will see more details afterwards. But as we have heard before, first of all, I need to understand, is this an event I want to match? And here, for example, I take simply the type of the event, and say, oh, event.type is of a value I want to understand to be an object of Prometheus I want to further analyze afterwards. When being now in the tree of Prometheus events, in the Tornado, I start my first action. And this is the iterator. So we now process further the array of alerts by taking the first element here, just as an example, simplified. The second one would come here, and so on. I would take now element by element and send it back by some simplification we applied here. It's a kind of extractor where in the terms of item, I take the alert name already, I take the description, some annotations, the status, all that stuff I'm interested in, and I send it back into a pipeline of Tornado to now really do what I want to do. I want to extract the information, the alert name, the namespace, which could become the host name. I could take the summary, which is the information what happened, maybe do some manipulation. For example, in the world of Openshift, I have the severity warning. In Icinga, I need to map this to some numbers. Warning is 1, critical is 2. Easy. Here, I have a preview. What is my severity, the host name, and that's all. In the action, I define this Icinga API call. As you know from Icinga, I can define the host and the service and also even the status by API. So I generate this output, specifying in the host structure an address, a template, and an object name with the variable name host name. The service name is the alert name, the alert rule from the Prometheus. And the action itself is the check result with the output and the status, which now allows me to receive exactly this information mapped to a service object and a host object in the Icinga world. For me, this closes the circle. Central alerting is possible. I can make notification, and I can make also availability reporting at the end. So let's try if I'm able to show this also on a real interface. Let's have a look. So I have here a simple Openshift cluster. It's local. What I have here, I have a deployment. This is my sample app, one pod, no replica, easy stuff. This is published over some routing, so I just click here so I can show you, oh, this is the web server, this is running, and it has typically this matrix exporter. So here you can see, these are at the end the values I'm interested in. 200 and the 404 error code. In Openshift, the Prometheus query language allows me to search for the HTTP total requests. And as you can see, we have multiple such web servers running, but the one which is of my interest is the namespace 1 or the Prometheus sample app, so simply add the filter. As we have learned before, just the label is Prometheus, and things are more detailed. I have now the web server, 6 normal requests, 0 wrong requests. Let's get things behave bad. I can do, let's see, I have a script probably here, yes. An error generator, so this is calling the website, but it's generating the calling an alias which does not exist. This one now is generating alert errors. We can see it also here. The application, the exporter, now is counting the values on the error side. And also my Prometheus recognizes, yeah, it's not as it should be. We will have an error sooner or later. This is obviously keep under monitoring. I have an alert rule in place, which is a user-defined alert rule. This one is the HTTP error rate here in the user space. defined. Maybe I just refresh so you maybe see already. Yeah, exactly. That's what I wanted to show you. Here it starts already the pending situation. So is it possible to read? Yeah. This is exactly the Prometheus query from before. 404, metric. And at the end, here I see this is still pending. And in my Icinga, in this case here I have the NetEye version. I have the Icinga interface. We don't have any host, Openshift from the namespace 1 created yet. But yeah, it's already happening. So we have the exactly the situation. The alert rule fired the event to the tornado. Tornado elaborated this, and here, 20 seconds ago, the new alert rule name is created as a service, and we have an incoming HTTP error rate alert for host namespace 1 on the pod Prometheus blah blah blah, which is being now tracked on the system. Let me give just a quick information how this is be done in Tornado. So Tornado does not show the single alerts, but allows the configuration. So I can just do the configuration and track how things are behaving. So the rule sets, which are here for interacting with incoming information. For each is the first level. I interact with the array, iterate with this for each operator on it, and send the single alerts back into the pipeline. When it's going back into the pipeline, one of these alert rules should match. It's a firing alert or it's a resolve alert. So it's not complicated, but it's quite just the way how to find it out. To make life easier with Tornado, these events are tracked in an archive. So let's make a tail of the archive of the original events. And is it possible to read? Because it's quite long. This is now an array, as you can see here. We have the alert array, first element, and potentially other elements are inside. In this case, we have only one. It's not exactly the problem for the HTTP, because I have multiple problems here. But don't get lost on this. Let me show you the second file. So this is the array, archive array. And I see that I got more than one. Error rates, this is the event. So just to let you understand, so this is a structure. We have a payload, we have data, and the single variables we extracted before. And to work now to configure such new rules, because maybe the event is different, something changes. The rule in Prometheus is not behaving with that information I want to receive, and my rule does not match anymore because of some regular expressions. I have here this preview editor, where I can simply copy-paste this message, fire it, and understand from the route to the various filters, oh, this is matching. And finally, the firing alert here is extracting from the JSON by saying event.payload.description the value, which is then, for example, exactly the text, description, hostname, and so on, which is then leading to what I've seen here in the monitoring. So it's the creation of the host. Exactly, now I have the second one. Plus, we are using also director. We create in the director itself the element, so in order that is persistent after the deploy. I would say that's enough. I hope also I'm not running out of time. So therefore, I would say let's go for the conclusions.
Thank you, Patrick. Well, first things first, we're still on the way. The goal is not yet fully reached, but we learned so much about Kubernetes, its metrics, its resource management, and so on. You can imagine during our POC with the vanilla cluster, we crashed Kubernetes here and there fully. With this experience, we learned at 85% of resource used in Kubernetes, Kubernetes stops working. Not really stop, but you cannot deploy anymore, you cannot read anything, nothing. So with this solution now, we were able to summarize and visualize all the needed resources. We filtered them before, as you saw in the PromQL, and now we are able to set meaningful limits to talk with our developers about resource management and share with them our little solutions. So RTL2 says thank you.
But we have two more conclusions from the project side. So this is an empiric approach. It has to be adjusted for the various environments. They can be different. But what we found out, Prometheus is quite flexible in defining the rule to extract whatever you want from the metric. You can be careful when defining which attributes you want to send to Icinga, but it's very flexible to do that. Don't send the metrics itself to Icinga. It's not made to send thousands of events per second over the Icinga API, but it's also not the right case for do that. We also in Würth learned about that we can improve the tornado. The iterator can be simplified from the user perspective. And last but not least, we did not cover the handling of log events, but we learned also yesterday there are other good approaches for Openshift and Kubernetes for doing that. To give you a giveaway, Tornado is open sourced. We have now rewritten the graphical user interface. As you have seen, this carbon design interface is new. We just released it a few days ago, also in a public space, so you can fully access to what you have seen for the part of event processing. Tornado is available on GitHub. We have also Docker Compose, so that should be easier. Otherwise, this environment is not that easy to build up because it's an API approach and it's interacting all together. And the use case we have presented is also documented by Red Hat. Is nothing we have invented from zero. It's no miracle. Is quite well documented, and you can also try to use and start from this if you're interested in trying this out for yourself. From this, thank you also from my side, and we're here for questions.